Hi everyone, in this video we will see how to actually pattern on a high resolution stack. Before watching this video, I recommend you to watch the previous video regarding high resolution patterning, which is a more general video where I explain to you how to pattern in high resolution, different approaches, how to tune the parameters to pattern in high resolution, so that you can have a better understanding of high resolution patterning. Here we practically see how it looks like patterning on a high resolution stack. Based on also on the previous video, we were trying to pattern these high resolution lines. Let's just remember remind to ourselves, and that the design that we imported had a 25 nanometers half pitch. And here we reduce the pixel sizes on X just to have a higher density of pixels on X direction. In the session, we saw previously that we were able to pattern such high resolution lines. Now we see how it changes on a pattern on a high resolution stack. In this case, we are using a high resolution stack with 50 nanometers of PMMA on top of a silicon substrate. On top of this 50 nanometers of PMMA, we have 2 nanometers of a silicon dioxide hard mask, which was made by spin coating and then barrel ashing to thin and form the silicon dioxide. And then we spin coated PMMA as buffer and adhesion layer, and on top of these 2 nanometers of PMMA, we spin coated 6 nanometers of PPA. So it's quite a thin layer of PPA. What do we expect? Well, first of all, when we pattern and we have a hard mask, it's really hard to pattern on hard mask with our cantilever. So we have to consider that we cannot really pattern much deeper than 8 nanometers, which is the total thickness of the PPA and PMMA combined. In some cases, if we use a very high force, very high temperature, we may be able to punch through the silicon dioxide hard mask because it's only 2 nanometers. And this is also much easier to do with the laser. But because we are actually making a resolution stack, we don't want to punch through this to this mask. So now let's see, by using parameters which we used in the previous video to pattern in high resolution, which kind of result we obtain first of all. So let's move a little bit and let's try to run this pattern. We are using 950 Celsius, 8 volt, forward height of 250, and in patterning parameters, we're using a force pulse of 1 microseconds, which I modified. And also, let's not forget that I changed the upsampling factor to 4 in order to have a better reading. So this was able to give us good results when patterning on thick PPA. In this case, we are on on the mentioned high resolution stack, and we also see that on the resolution stack we have quite a good pattern. So we see that the lines are well separated. Maybe some are not deep enough, so maybe we can try to increase the depth to the force to 8.5. Or 9. We move a little bit and we see what happens. So we expect to pattern deeper, first of all, or a little bit deeper, in this case, not much deeper. One thing to keep in mind is also when patterning on high resolution, the repeatability sometimes is not so high. So here we're still patterning decently, but not as expected, I would say. But what I would like to show you is, first of all, how can you believe me that we are patterning on a high resolution stack? Well, I told you that we cannot really go deeper than this 6 nanometer of PPA plus 2 nanometers of PMMA. So a way to test this is, first of all, let's try to increase the temperature quite a lot, or let's try to put the force pulse to a value that's a normal value of 5. And because 5 is quite, I mean, these values combined will result in a very deep pattern. I also reduce the force because I may use too high force. So let's try to run this pattern again. With a force pulse 5 times higher, I expect to pattern much deeper with a 9 volt. Maybe if I pattern on a thick PPA, I will pattern 80 or 90 nanometers deep. But let's see here what we actually see. And I can also increase the force while we pattern to see. And even if I increase the force, quite high values, here we're using 9 volt, and a standard force pulse time, we are not able to pattern deeper than these 6 nanometers. Probably the total thickness of PPA and PMMA combined is even less than 8 nanometers. Looks like it's probably around 6. So a very thin layer of polymers on top of our hard mask. And to give you further proof of this, I can even increase the temperature. Let's say I put 1100 Celsius. Oh, put 1100 here. And we run again the pattern. So I increase the temperature by quite a lot, 150 Celsius. This should really make our pattern deeper. But we will see that it's not going to be much deeper because there is a hard mask that's blocking us. And can it be actually deeper? Yes, but only if we punch through the hard mask, and it's not really recommended because this will damage our tip. It can happen if you use very high force and very high temperature, which is probably what we can see in this case. So maybe I reduce again the temperature. So in this case, we're already sticking, and in some cases we may be punching through the hard mask, so not really nice result. I may have to increase the forward height maybe to 280 because of some possible thermal bending, or 290, why not? Here we can see some sticking also, which means that rather than punching through, not able to properly lift the cantilever because of a thermal bending effect. So let's run it again. Let's also check our tip. When we pattern on a high resolution stack, especially if we are scratching on the silicon dioxide surface, we will consume our tips more than a standard pattern on PPA, because silicon dioxide is of course much harder than polymer in general, and it's also harder than silicon. So silicon versus silicon dioxide will cause some wear of our tip. Here we can see better with a much higher temperature and slightly increased forward height, that we're not able to go much deeper than 7 nanometers. So probably here we have our hard mask and we cannot go deeper than this. And if we use the same parameters on the PPA, on a thick PPA sample, we will pattern much deeper. Actually, the sample of PPA is in this direction, with just PPA, sorry. So let's try to see if I move to the sample, to that sample using these exact same parameters, how deep we will pattern. And we can also check here, there are the previous patterns that we did in the previous video. So let's try to move here in the exact same location. We quickly do an approach. And we try to pattern with these parameters. My guess is that we will pattern deeper than 50 nanometers, maybe between 50 and 80 nanometers. But let's see actually how it will look like. So here we're doing the approach. In this case, as I mentioned in the previous video, we have a sample with 10% PPA. So the total depth, the total thickness should be around 180 nanometers following the spin coating tables. The approach is almost done. The tip is still in good shape. Now it's time to test this pattern as soon as the sample level plane is done on this other sample. So in this case, we have a maximum scan height of -40. So if we pattern deeper, we cannot really know for certain the largest depth that we're reaching. And we will see that the lines are probably going to merge because the force is too high. Force and temperature are too high to have them separated. So in this case, you see holes, merged lines vary because the force and the temperature are quite high, even if the forward height is increased from standard values. So this is just to prove you that there was a hard mask in the previous sample. Maybe you don't believe me, but also to show you like how it would look like on a sample with a thick PPA. So the hard mask is really stopping our tip when trying to go deeper. And the more we pattern on this kind of high resolution stacks, also the more we can damage the tip because of its contact with the silicon dioxide mask. Now let's lift the cantilever again, and let's go again to our high resolution stack. And let's do an approach. One last thing that I would like to discuss and show you is using the laser. Of course, when we use the high resolution, now we're doing an approach in the meantime. When we're using a high resolution stack, we want to pattern in high resolution. So the laser is not really high resolution, but if we have a nanofraser with a laser, then we can also use it to pattern, let's say, part of contact paths that we can still do with a high resolution stack. And we may want to do some mix and match between laser and TSPL. So one important thing to keep in mind is that the hard mask will not make us write deeper than this, let's say 7, 8 nanometers in this case, unless we use a very high power that punches through, make the laser punches through the hard mask. So this may cause some issues in the configuration of the laser, for example, because as you can see here, this is the last step of the laser config that I ran earlier on this stack. And you can see that the software struggles to detect these holes because they are not very deep. So we can check that the depth is around 7, 8 nanometers. 7, 8 nanometers. So these are not very well detected. So first of all, this laser focus step may not be very accurate. We can also run it again to see live what happens. And in this case, we may have to manually adjust it so that the position of the laser spot is accurate. So these lines should actually pass through these sets of dots. Because as you may have seen from the previous training videos regarding the laser configuration, the laser focus step also allows us to find the best position, the most accurate position for the laser spot. So this is one thing to keep in mind. Another thing to keep in mind is that it's usually better to perform some laser dose tests in order to check which power we should use to write on the high resolution stack, because again, we don't want to punch through the hard mask and pattern much deeper than needed. We just want to remove the top layer of PPA and PMMA to have a successful transfer process. So in this case, you see that the depth is only 6 nanometers, maybe 7, and the software does not really see these dots because it expects much larger depth in the range of, I don't know, at least larger than 10, 15 nanometers. So what we should do here, we can manually adjust this. So we see that on X, the position is a little bit shifted. So we can, let's say, press -1. Here, seems like there is a small software bug. So maybe let's skip this for a second. But what you should do is changing these parameters so that these two lines will move and then they are centered with these dots. So as I mentioned to you earlier, it's a good thing to do a laser dose test. What we can do is also seeing what happens when we pattern with the laser at different temperatures. So I import a design. For the laser, so we put laser parameters, let's put it that way. So 100 nanometer pixel size, and we want to have a minimum power, let's say 30. 53 is a little bit silly. Let's say 50. And the maximum power, let's put 300. So you can see here we're going to start from 0, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So because we have 16 squares, so we have very different values of power of the laser, and we may be able to see if at some point we're able to punch through the hard mask. In this case, the geometry is a little bit larger than the scan range, so we can try to put 0.7 to make it fit the range of the scanner. So then we go to the laser layout, put this here, and maybe we can also increase the pixel time to 150. So when we punch through the hard mask, we should even be able to see this optically, because we will start removing the underlayer, which in this case is PMMA, and it will look optically much different. So let's see what we can see now. In this case, we start from the lower values of power, and already here we can see that it's the left side is a little bit brighter, and when we increase the power, so probably here we start punching through the hard mask, and here on the top, when we are around 200 to 300 milliwatts, probably we were able to punch through it everywhere. We can try to also run it again, maybe with quite higher pixel time. Maybe we put 400 just to see if it changes a little bit, but I think this already proves what I was trying to tell you and explain to you. And in order to confirm this, we can, of course, read this with the nanofraser to have an idea of which kind of depth we are reaching when we're punching through the hard mask. So here we're writing more slowly because I increased the pixel time, so we're spending more and more time for each pixel, in this case 400 microseconds. So this means that if we punch through the hard mask, we should be able to punch through even better. Even though it seems like it's not the case. Okay, here it looks better. So let's try to have a read of this laser pattern, just to say confirm what we were mentioning. So going to read arbitrary, we place something here, pixel size y can be, let's say, 60. Okay, maybe 125 should be good. And we decrease the scan height, let's say, to minus 70. So in this case, as mentioned to you earlier, we have 50 nanometers of PMMA, 2 nanometers of hard mask, and 80 nanometers of PPA plus PMMA. So we cannot really write deeper than the sum of all these thicknesses combined, which is around 60 nanometers. So by putting the scan height to minus 70, we are sure that should be able to read pretty much everything. So here we can already see that we are reading indeed deeper. Probably didn't place the read region in the best way here. So let's try to move it a little bit and read again. So here we are reading these areas where basically we're patterning at, let's say, 300, 280, 260, and maybe 240 milliwatts. And we see already that we have quite a difference in the depth. So here pretty much should be the hard mask, and then by increasing the power we are able to write deeper and deeper. So here we are punching through the hard mask with the laser. And I can also maybe do a read in the vertical direction. So let's say here. So in this case, we should see a little bit better when we are not punching through the hard mask, because we are reading across power that is, let's say, around 70, and here we are 300 milliwatts. And indeed, we can see that here we're not punching through the hard mask, patterning at 6 nanometers or so of depth. Here probably the leveling is not the greatest, so I should extend it a little bit more this region. But anyway, the point is here no punching through the hard mask. Here we see a clear punch through the hard mask with the laser. And these are just some inputs in order for you to be more aware of also how to effectively pattern with the laser on a hard mask. Here we practically see in this video how to pattern both with the SPL and both with the laser on hard mask. on a high resolution stack with the silicon dioxide hard mask and 6 nanometers of PPA on top of 1 nanometers of PMMA. So I hope this was also helpful for you to understand a little bit more how to practically pattern in high resolution. And I hope it will help you for your research.